let's see what we got here. Medium. Successful pairs of spells and potions. I think I saw this, maybe. You're given two positive integers arrays, spells and potions of length n and m respectively, where spells at I represents the strength of the ith spell, potions at j represents the strength of the jth potion, and you're also given an integer success. The spell and potion pairs considered successful if the product of their strength is at least success. Return integer array pairs. Length n, where pairs I is the number of potions that will form a successful pair with the ith spell. Return integer array pairs. Interesting. Okay, spells 5, 1, 3, potions 1, 2, 3, 4, 5, success 7. So the product of the spell power and potion power is 7. So 5 would work with 4 of them, 1 would work with 0 of them, 3 would work with 3 of them. Okay. 3, 1, 2, 8, 5, 8. Spell power product is 16. 3 works with 8 and 8, so 2. 1 works with 0. 2 works with 8 and 8, so 2. Okay. Seems reasonable enough. Let me think here. I feel like I want to sort. I feel like we should sort here. Sort, right? How many spells, potions do I have here? 10 to the 5th of each. If I sort, it should be kind of a 2-pointer deal. 2 pointers where the pointers are at some index for the spell power and potion power. Because if you have a certain spell power that's increasing, then the potion power that you would need would be a decreasing index. So if you sort the spell power in increasing fashion and potion power in decreasing fashion, then you have like incrementing 2-pointer deal where the ith spell power will work with the jth potion power or earlier, and you're always incrementing the spell power and the decreasing the potion power needed. Okay, I just need to keep track of where the original indices of these things were. Maybe pairs at I corresponds to the ith spell, so the output matches the spell numbers. Let's say answer equals 0 times n, where n is the number of spells. I think I need to keep track of what the index is. So sort spells is going to be an array of spell power of tuples of spell power and index that was originally found. So for every spell, for every index in range n, sort spells append the tuple that is the spell power, which is going to be spells at this index, and then I sort spells sort. Go ahead and just print that out to make sure it's okay. So this should be like 1 1 3 2 5 0 1 1 3 2 5 0. And this one should be 1 1 2 2 3 0. Okay, so that's sorted. And now I need to do these like reverse sorted for the potions. Sort potions. And this is going to be tuples of potion power. I guess I just need to count the number of potions that match. I don't know. Don't need to know the indices. So I think I just need potions that sort reverse equals true. And then this is going to be, let's go S pointer and potion pointer is 0. It's 2 pointers for current spell and potions. So if I have spell 1, then I would need to go to the potion power that would multiply to be greater than equal to success. So for every index in range n, let's get the tuple from the spell, from the sword spell. So S power, spell power, and S index is the spell index. From the sorted spells at this index, and then while I guess S pointer is the same thing as index here. So S pointer, while the potion pointer is less than the length of the number of potions. I'll make a dummy thing to prevent having to use that condition every time, but and the multiplication of this is greater than success, and S power times potion power, which is potions at this pointer, greater than equal to success. The pointer increments. So at that point, the pointer should have the index of the number of potions that would be successful with the spell. So answer at the S index for this thing should be where the pointer is. Okay. And okay, let's actually return the answer to make sure that works. Misspelled success. Doobie doobie doobie. Okay, that worked. Okay, that worked. So I think I can add some dummy value to the end of the potions array so that it never goes past this. So I think if the last potion power is 0, then that can never be successful. Or maybe -1. Potions append, I guess 0. Success is probably always greater than, yeah. Success is always greater than 0, so should be a good dummy value. Should make it slightly faster, so like one less, well, in theory, if not in practice. Okay, I wonder, I'm doing a double sort. I'm sorting both the spells and the potions. And I wonder if there was a way for me to do this with only sorting one. Maybe. So if I just sorted the potions themselves and kept the spells the same, it wouldn't have necessarily a strictly increasing pointer. I'd have to do like a search for a certain value corresponding to that. So I have to like search in the sorted array something that is like 7 divided by 5 or something along those lines. So it had to be, it would take sorting the potions and then doing the spell number times log of the number of potions. Since I'm going to be doing a binary search in the number within the potions list in that case. Yes. The other thing is if the potion power is I mean, the other thing is I could calculate the necessary success value once and then compare the potion power to that success value rather than do a bunch of multiplications. maybe that might be slightly faster. There's less calculations, I guess. Need power is going to be success divided by S power. Rounded down maybe. That's fine. And as long as the potion power pointer is greater than the need power. Guess that might be slightly faster. Oh boy. Might be faster, but it's not even correct. This S divided by S power. And if I divide both sides of that inequality, what S power would be success divided by S power? Why did this not work? Let me think. So what did this return? 504 302. 504. So initially this was 7. 7 divided by 1 is 7. So the needed power for the potion was 7. And there was nothing that matched that, so that's fine. So that gave me the 0. And then the next one was 3. 7 divided by 3 should give me 2. Rounded to integer, or rounded down to integer, truncated. 2 should be 5, 4, 3, 2. Index should be at 4. Okay, let me double check this. Three should be like 0, 0. S power was 1. Oh, okay, S power is 1, 0, that's correct. And then 3 gave you 4. 3 should give me 3. 5, 4. Okay, yeah. Cannot be rounded down. Has to be rounded up. Success divided by S power. 7 divided by 3 should be 2. But 2 times 3 should be 6 only. So it needs to be at least, it needs to round up. Guess, I forget how I do this. Round, maybe? No, it has to be round up. Ceiling? Is it ceiling? Seal? Not sure. There should be a way to do this without using ceiling. I think ceiling's a little slow. Okay, that's slightly faster. Let's see. Python round up division. Numerator plus denominator minus 1 divided by denominator. Is this faster? Works correctly for positive numerators and denominators. Is method 2 without ceiling faster than method 1? Okay. I assumed it was. I don't think I recall seeing this before though. Numerator plus denominator minus 1 divided by denominator. Guess it goes, so it goes an extra level up, minus 1. I think I understand that. I don't think I remember it though. So it'd be something like the needed power would be SSS plus S power minus 1 divided by S power. Alright, it doesn't do anything here. In theory, if not in practice, it was faster. So calculate the needed power, compare to the needed power. Get that number. And then put that number into the answer array. Is there a way for me to not sort the spells maybe? Three, 1, 2. Five. Yeah, it's outside of doing a search, binary search for the appropriate potion power within the sorted potions array. Or maybe doing sorting the shorter sorted list between spells and potions, and then doing the binary search within that for the longer list. I guess that might be somewhat faster. It'd be like the minimum of m and n times log of the maximum of m and n, where m is the number of spells and n is the number of potions. Something like that. Alright, I think I've optimized this up to the point where I'm done. So summary, this is use of sorted arrays to make it easier to identify the number of potions, number corresponding number of potions corresponding to a spell power. This is as a or also used two-pointer technique to not search over the same space of possibilities. So the overall is sort each array. So the kind of example, a sample case would be like your spells are, let's say, 1, 2, 3, 4, and your potions sorted in verses, say 12, 8, 6, 5, and the success is, say, 10. Then 1 would match with 12, 2 matches with 6, 2 goes up to actually let's go further down, I guess. 2, 1, 2 matches with 6, 3 matches with 5, no, actually 2 matches with 5, and 4, right, 2 matches, 3 matches with 5, 4 matches with 3 in terms of if you have spell power 1, then there's 1 potion, 2, then there's 4 potions, 12, 8, 6, 5, 3, there's also 4 potions, and 4, there's 5 potions. So consider that a spell pointer matches with an increasing potion pointer to result in a pair that exceeds that is at least the success power. So that's pretty much like it. So sort the potions increasingly, or spells increasingly, potions decreasingly, find the appropriate potion placement, potion power, potion pointer placement for the spell, for the current spell power. Value matches the number of pairs that work, and then place that back place that into the answer array at the original spell index. Sort spell, sort a copy of spell lists of tuples where you deal with spell power index of that spell to keep track of original index. Because this would have been a lot easier if the spells were kind of already pre-sorted, but if you don't have that, but you still need to know the original spot or to know where to put it, then yeah, create a tuple list. Sorted spells. Time flexi, this can be O of O of n log n plus m log m, where n equals the number of spells and m equals the number of potions as each list is sorted. The 2-pointer portion is O of n, I guess. O of n plus m as the pointers increment to the end of the respective arrays. It's possible that there was a solution that solved in O of, like, I want to say min of nm log max of nm time, where you sort the longer array and used binary search for the necessary value based on the other array. There was, I think, a possibility of doing that. In general, I think this is marginally gain. I think this is of marginal gain. Space complexity is going to be O of n to have a copy sorted spells tuple array. I think that's the only thing that was necessary. The answer is